So we're looking at applying Newton's second law, F equals ma, and potentially Suvat to pulley type questions. We need to first of all understand what a pulley is. If you look in the room, the blinds, they are operated by a pulley system with a string attached on either side of the pulley. So pulley is something that is just circular usually, and you've got like a rope passing over it like that. And the rope is the pulley will have a kind of like a pivot. It's connected at the middle by some sort of pin. And so then the pulley moves or spins on its spot. Now we assume that the pulley has zero friction, i.e. it's completely smooth. So when they say smooth pulley, it means there's no resistive forces, that the pulley spins freely without any friction. So that's kind of what a pulley is, and a string passes over it. So before we even go into the question, we need to understand then what that smoothness actually results in. So as you can see in the question, it says the string passes over a small, smooth, fixed pulley. Now the smooth fixed pulley is very important. That word smooth essentially means that whatever tension we have in the string on this side, suppose we've got a tension here, then we will have exactly the same tension on the other side because it's connected by the same string and it passes over a smooth pulley. Now, if there was friction there, that will result in the tensions being different. So you can guess what a 1 marker question would be. How have you used the information that the pulley is smooth? What's the answer? You assume that the tension in the string on either side of the pulley is the same. So that's what the word smooth means. Tension on either side of the pulley is the same. So that's usually a 1 marker question there, testing your understanding about modeling assumptions. So let's go to our question then. We now understand what a pulley is, and we understand what the word smooth means, and that it's frictionless. It goes on to say here, particle P and Q of masses 2m and 3m, m being an unknown letter, are attached to the ends of a light inextensible string. We know what the word light and inextensible means for string. We've come across it before. Light means what? The tension is the same throughout. Inextensible means acceleration between the two objects that the string connects is equal. We've already come across that before. The string passes over the smooth fixed pulley. Write down the equation of motion of P and Q. Okay, it's gone on to the question. Before we go into the question, I need to represent all of that information into a diagram. So it looks, I'm going to get rid of these tensions. I'll draw them in later. First thing which I'm going to do is just draw my pulley with the string passing over it. I'm going to draw a particle just by representing it using a box. I'm going to call that particle P, as they said. What does P have a mass of? P is 2m. So its weight is what? 2mg, acting downwards, 2mg. I've got a mass of 3m on the other side, which means its weight is 3mg acting downwards there. When those objects are on the pulley in that way, the string is in tension or compression. Tension, because it's kind of in a stretch situation, right? So which way is the tension acting? If I was to draw a tension force here, tension acts which way? What did we write down? Tension acts away from the object. There. I know I drew it earlier downwards, but we've got to understand why I drew it earlier downwards, because back then, did I have my objects drawn? What was my object back there? The pulley. So which, if I drew another tension, it would be acting like that, away from the pulley. Here, my tension is acting away from the object. This tension is acting away from P, whereas this tension here is acting away from the pulley. So I'm drawing this tension here is the tension felt by the pulley, whereas the tension that I've drawn here are the tensions felt by the object. Now, There is a question where sometimes in part E, the very last part of it, part D, part E, whatever, they ask for the force on the pulley. If they ask for the force on the pulley, you would have to just look at that top bit and look at the, can you see a tension acting down and another tension? So there's in total, what's the total force acting on the pulley? 2T acting downwards. Can you see? T, both of them acting downwards. That's usually a 1 marker question. Sometimes they ask 1 or 2 markers, usually right at the end, about the pulley. But for the majority of the question, we're not at all interested in the pulley. So yes, you can draw that force, the tension there. It's not a problem. We'll draw it for completeness anyway. Okay, leave it there. Now, it goes on to say something else. The system is released from rest. What does release from rest mean? Starts from 0 velocity, and then it will start to what? Accelerate. If something picks up speed, it's going to accelerate. We need to decide, first of all, which way the pulley is going to move. By using a bit of common sense, looking at some of the weights, which one is heavier? Okay, so it's going to want to go which way? Down here. Yeah, I'll indicate that using a double arrow for acceleration. What about on the left-hand side? Which way is it going to move? Is it the same acceleration? Why? Inextensible string. So we'll call it the same thing here, A. So really, what is this system doing? It's moving which way? Which way will we take as positive? If we go with the idea, what I said about to choose the direction of positive. Which way do we take as positive? What do you mean by right, Isa?
If you were to look at this,
yeah. Okay, so Isa saying that it will move, or for this side it's moving up, and for the other side it's moving down. So the direction that we take as positive is like that, in that direction of motion. Okay, that's very important. Do you understand what it's doing? It's moving up that way and down that way. So I've just indicated it using that arrow, the way that the pulley is spinning as positive. So now that I've got my system with all my forces in, I'm in a situation where I can go to start applying F equals ma. Okay, now you're going to look at F equals ma. Now the F equals ma that we've done for previous particles connected is no different to this. It's the same idea. We can look at it as F equals ma applied to particle P. We can look at it as F equals ma applied to particle Q. Or we can look at it as F equals ma applied to particle P and Q. So let's go and apply F equals ma now. What's the question asking? It says write down an equation of motion. We need to understand what this word equation of motion means. It's often asked, and they often ask you to do that. So you might not know what an equation of motion is. Equation of motion is referring to Newton's second law. If it says write down equation of motion for particle P or Q, it means write down F equals ma for particle P and Q. That's what it's saying. In which direction though? The word motion should be the giveaway. In the direction it's moving, in the direction of motion. Write down F equals ma for particle P and Q in direction of motion. That's what it means by equations of motions. So make sure you understand the phrase equation of motion. Yes, you're going to get 2 equations. So here it said write down an equation of motion for P and for Q. It should have, yeah, maybe we'll correct their English. Write down the equations of motion. Yeah. Here it's for both of them. So we're writing 2 equations, yeah. So you can tell it's a maths teacher who wrote down the question, right? Okay, so we're going to go and apply F equals ma, but we're going to apply it to each particle. Remember, we never start by writing F equals ma without stating what we're looking at. We're going to look at particle P first. Which direction should we take as positive? Direction in which is moving. So if I'm applying F equals ma to particle P, which way should I draw my arrow? Up as positive. Thank you. F equals ma. Now I'm in a situation where I can apply F equals ma to particle P. Look at particle P. Tell me what other forces I should be writing down. What should I write down for resultant force? T minus 2mg equals, what's its mass? 2m and times A. Done. That's the equation of motion for particle P. Now we're going to look at particle Q. Which way am I taking as positive? Very good. F equals ma. Tell me what I'm going to write down for particle Q. 3mg. Be careful, we're taking down as positive. 3mg. 3m times A. It's the same A, so I've called it the same thing. That's part A of the question. Write down an equation of motion for particle P and for particle Q. Part B goes on to say find the acceleration of each mass. Well, it's the same, isn't it? We know. Now notice here I've got two equations, two motions. That's essentially doing F equals ma on individual things. What could I do with those two equations if I want to find out the acceleration? Yeah, so we want to find out A, so you might eliminate T. How else could we have done this? We could have treated the whole system together. Should we have a look at whole system together? Okay, I know it doesn't ask me, but I'm going to go and look at the whole system together. So I'm going to look at particle P and Q. I'm going to apply F equals ma, but what is my direction of motion for particle P and Q? Is it up? Is it down? How should I indicate it? Like that? That's better, isn't it? Because then I can see clearly which it is. So let's look at both of them together. Tell me what's been applied to particle P first. What's been applied to particle Q? Plus 3mg and minus T. Did you understand that? We need to look at direction of positive being up for one of them, down for the other. Is equal to, what's the total mass? What's the total mass? 5m times the acceleration. What happens here? Yeah, simplifies T minus T. 1mg, which is just mg, is equal to 5 ma. Divide by m on both sides. M is a constant. G over 5. G is 9.81, yeah? Is equal to A. We found out the acceleration. Now, I know I did it whole system together, particle P plus Q, but could I have done it using the individual equations as well? Yeah, it's the same thing as before. Remember when we looked at connected objects horizontally? It's the same thing. You can solve them simultaneously, or you can look at the whole system together. So what is really a pulley system is essentially a glorified connected system, a car trailer situation, but a car trailer acts horizontally, but a pulley is doing this. If I was to take this pulley and stretch it out, it would look like this, wouldn't it? Wouldn't it? Yeah. This being my 3mg. And there, do you understand that? But sorry, not 3mg there. I'd have a 3mg acting that way. I'd have the 2mg acting that way. If I did stretch out that rope, that's what it's going to look like. And then I'd still have my tension. And doesn't that look quite similar to a car trailer scenario? You just get rid of that pulley. There you go. It becomes a car trailer. So all that is just acting on a pulley. That's all it is, right? So don't be thrown off by it. But I think it's better to draw it as a pulley and do it this way. So we worked out the acceleration, brilliant. Part A done, part B done. Then it goes on to find the tension in the string. What do we do here? Go to one of the equations. Will you use that one here, maybe? T minus 2mg is equal to 2m times acceleration. The tension will be in terms of m. If they give you an unknown m such as that, don't be afraid to leave your answer in terms of m. They don't always ask, leave it in terms of m, but if m is just given as a mass, treat it as that. So you're going to have T is equal to 2mg over 5 plus 2mg. Tidy it up a bit. That's the same as 2 over 1 or 10 over 5. 10 plus 2, 12 mg over 5. You can use your calculator, just find out, replace g with 9.8, get a decimal, leave it in terms of decimal, it's fine. Usually in mechanics, answers should be written to the least degree of accuracy that you're using. So gravity, you're using 9.8. How many? What's the significant figures that we're using for gravity? 2. So usually we state all our answers to 2 significant figures because that's the most accurate measurement that we used, or the least accurate measurement, I should say. Yeah. So we found out our tension. Find the tension in the string. Yeah. So now that we know our tension, let's go and look at the next part. It goes on to say, find the force exerted on the pulley by the string. So remember what I said earlier about the force exerted on the pulley. So now we need to draw what? We're looking at which bit? The pulley. The force exerted on the pulley, just draw the pulley and draw the tension acting like that. There. So there's my pulley. What is the force acting on the pulley? Yeah. Force on pulley is 2 lots of tension acting which way? Acting downwards. And what is 2 lots of T? Well, it's 2 lots of 12 mg over 5, which is equal to 24 mg over 5. There's my force on the pulley. Acting downwards. Don't ever say a force without stating its direction in this case. Acting downwards, yeah. And then it goes on to say, find the distance moved by particle Q in the first 4 seconds. What we're using here? Suvat. Why can we use Suvat? What tells us there's constant acceleration? Suvat is only used for constant acceleration. Why is there constant acceleration? String and extensible means acceleration in one object is the same as the other. It doesn't mean constant acceleration. Newton's second law, F equals ma. Why is acceleration constant? F equals ma. If you expect acceleration to remain constant, what else do you expect to remain constant? What force? The resultant force. Are any of the forces changing? No. Mass is constant, it doesn't change. So we can use Suvat as long as acceleration is constant. Acceleration will be constant if resultant force is constant. So you need to remember that if resultant force is constant, acceleration is constant. If acceleration is constant, resultant force is constant. That implication you need to remember at all times and you need to pick up from questions as to when you can use Suvat. So let's go and do this first for the first 4 seconds. So we're going to do Suvat as the particle Q, distance moved by particle Q. Which way is Q moving? Well, it moves from this point here to some point down there. So I'm going to call this point A and I'm going to call this point B. What happens between A and B? It moves by how much? It goes to that point, doesn't it? So I'm going to write down, remember what we write down usually? We write down A to B. Which direction are we taking as positive? Down as positive. For A to B. For particle Q, isn't it? Following? Particle Q. I put A at the original starting point, B as where it's going to end up after 4 seconds. It's going downwards. We're looking at particle Q. I've indicated particle Q. I've indicated A to B. I've indicated down as positive. I'm going to write SUVAT. What is my S? I don't know. What's the initial speed? 0. What's my final speed? Do we know? No. What's my acceleration? No. When is it 9.8? Only if the object has no other forces acting on it. We worked it out. G over 5. Remember what we said? An object will only have gravity if there's no other forces connected to it, but there's a tension connected to it. So acceleration is g over 5. Positive or negative? Because we took down as positive and q is moving downwards, acceleration then. Okay. How long is it moving for? 4 seconds. Questions asking you to find out what? Find the distance, find s. What would we use? Yep, this equals. U is 0. Half times g over 5 times t squared. So s is equal to 16 over 10. 16 g over 10. Which is the same as. Right? Whatever that is, state it to 2 significant figures is fine. 15.68. Yeah? You could write it as 16 or 15.7 would be accepted. Sometimes students state it to a higher level of accuracy than 2 significant figures. It's fine. Okay, but don't state anything less than 2 significant figures. There you go, complete question. Okay, so we've seen a pulley question. It is simply applying F equals MA and so forth to that particular scenario.